Okay, so let's learn another pivoting strategy in Gauss elimination method, and this strategy is known as scaled partial pivoting. So if we want to solve a given system using scaled partial pivoting, the first thing is we write the augmented matrix, and after that we identify over S1, S2 and S3 from each row of this augmented matrix and without including the last column. This is not included. So my S1 will be the largest entry from the first row in absolute sense, and 4.21 is the largest entry. For S2 it will be the largest entry in row 2 in absolute sense, which is 10.2, and for S3 the largest entry in row 3 in absolute sense, which is 1.09. Okay, so after identifying S1, S2 and S3, which in this case it's a 3x3 system, so I'm going to have S3, 3S. So next thing I'm gonna do is that for the first column, I will divide every entry of the first column with its corresponding S. So for A, I will divide A11 with S1, A21 with S2 and A31 with S3. And then from the answers of these, I will decide which one is the greatest in absolute sense. After doing this, I came to know that 1 is the largest in this case. So from here, I get the indicator that the third row should be interchanged with the first row, and after that we will apply usual Gauss elimination. So according to scaled partial pivoting, this 1.09 should be the pivot entry of the first row. So moving forward, after interchanging the row 3 with row 1, because of this concept, my new matrix will look like this after interchanging the rows. So after interchanging the rows, I will apply the usual Gauss elimination method to make this entry 0 and this entry 0. I will find my multiplier and then I will subtract this row from multiplier time row 1, and same goes for the 2.11 entry. I find the multiplier and then I subtract to make it 0. So to move forward after this step, I have to decide between these two that which entry is going to be my pivot entry. For this I have to first identify my S2 and S3. Keep in mind that these S2 and S3 will not be the same that we found here. The new S2 and S3 will be from the matrix after interchanging the rows, this one. So from here, my S2 should be the largest entry in row 2 from here to here, and S3 should be the largest entry in row 3 to here, and I told you earlier that the last column is not included in this. So if I decide my S2 and S3 from here, my S2 will be 10.2 and my S3 will be 4.21. And then again, I will divide this entry with S2 and this entry with S3 to get the answers, and from these answers I will decide that which entry should be my pivot entry. So in this case 1.4541 has the largest magnitude, so this indicates that my third row should be interchanged with second row, and after doing this I get something like this, and now this is my pivot entry. After this I will apply my usual Gauss elimination method to make the entry below the pivot entry 0, which in this case is this one. So I want to make it 0. I will find the multiplier, and then row 3 minus multipliers times row 2 will give me my upper triangular system, and I can apply back substitution to solve this system. That's it. So from back substitution I got the x3. By putting this x3 in the equation above, I get x2, and by putting this x3 and x2 in the first one equation, I got my x1. So this is the concept of scaled partial pivoting in Gauss elimination method. Now we are going to develop the MATLAB code of this thing. To develop a MATLAB code, I am going to take help from the code that I built earlier, which is Gauss elimination with partial pivoting. I am going to copy this code to a new script file. If you do not understand Gauss elimination method or Gauss elimination with partial pivoting, you can just watch the video of Gauss elimination method with partial pivoting. So I'm not going to explain the things that I explained in that video. So let's start building the MATLAB code of Gauss elimination method with scaled partial pivoting. So the first, I should have the coefficient matrix and the source vector from the user, and after that I will determine the dimensions of my matrix, and then I will introduce a vector of unknowns in which I am going to get my unknowns. So the first step is going to be I will augment A given A matrix with B, and I am storing it in AUG variable. After this, in scaled partial pivoting, what we do is we find over S. The first thing is we find over S. Since we are going to make this code general, so we are going to use the loop for this purpose. For k varies from 1 to total number of unknowns, because we have first time we have the S equals to the number of unknowns. Like if we have 3 cross 3 system, we have 3S initially. If we have a 5 cross 5 system, we might have 5S initially. So my k will start from 1 and to number of unknowns, and here I am going to find my S vector, which is going to be like S kth value should be equal to the maximum value in absolute sense of what? Of augmented matrix kth row and the columns from 1 till total number of columns. So for the first time, k will store 1 in it, and my S1 will be like maximum value in absolute sense from the first row till 1 to n column. So in other sense, from first row, first column, first row, second column, and first row, third column entries, the maximum entry will store, the maximum entry in absolute sense will be stored in S1. And this will give me S2 and S3 as well. So after this, I want to do scaled partial pivoting. So for scaled partial pivoting, I'm going to edit something here. After identifying my S, my next step is to divide each entry of that column with their corresponding S values. So I'm going to divide by using loops. So again I will use a loop here for A. For example, A varies from J to N. I will explain why I'm starting this loop from J to N, and I'm storing those entries after division in variable d. So d a value should be equal to augmented matrix ath row jth column divided by the corresponding s, so that will be SA, and my augmented value should be in absolute sense. So this thing will store the entries of each column dividing with their corresponding s into a variable d or a vector d. I am starting this loop from a varies from j to n, because when we move in the next iteration, or we can say when we move to the next pivot entry, second pivot entry, we only find the two s, only s2 and s3. So we are not interested in s1 in that case. So that's why I'm starting this loop from j. So in the next iteration, you can say when we will be on the next second pivot entry, my j will have the values 2, and in that case a will start from 2 to n. So now we have to identify the which entry is the maximum in this vector d. Like we decided here, from here, that which entry is the maximum from all of these. So for this, we are just editing this line of partial pivoting, like we are interested in finding the maximum entry in absolute sense of d from j to n. Since I have already used the absolute in the above line, so there is no need to use the absolute here. It is obvious that the entries will come in absolute sense till here. So I am interested in finding the maximum entry of d vector from j to n. Like if I'm deciding for the first partial for the first pivot position, then my j will be 1, and then I am deciding the maximum entry from 1 to n. And when I am deciding for the second pivot entry, my j will be 2 in that case, and then I am deciding the maximum entry of d from 2 to n, and I am ignoring the first s, you see. You can learn further about this command in my previous video related to Gauss elimination method with partial pivoting. So this command will store the maximum entry in variable capital M and the position of that maximum entry in P, and after this, these three lines are doing nothing but the row exchange. So these lines are making row exchange possible. So after doing the row exchange, I will just apply the usual Gauss elimination method, and I'm not changing anything into it. But the important thing here is that after row exchange, I also identify my new S positions. Like you see, after doing row exchange, I decide my S2 and S3 from this new matrix after exchanging the rows. So after exchanging the rows, the first thing I should do must be getting my new S values. For this I am copying the loop that I used for S values outside here inside, and my this loop for finding these new X should start from j to n, since if I'm finding the second if I'm deciding for the second pivot entry, so I should not find the s1. So in that case j might have the value 2, and I will only find s2 and s3. Also I should not use the semicolon here to see what is happening, when I will test run this code. And I should also introduce the dimensions of S initially to just avoid the errors if my workspace is not clear and S might have values in that case. So I'm initially introducing the S with zeros of the dimensions equal to the dimensions of B. So that's it. This is the code of Gauss elimination with scaled partial pivoting. Everything else will be the same. The how we perform the Gauss elimination method and how we perform the back substitution, all things are same. If you don't understand these things, you can watch the previous video of Gauss elimination method. So let's test run this code. For test run, I should name this code. It should be Gauss scale, something like this. So let's run this. So the code is demanding a coefficient matrix from me, and I should enter that coefficient matrix that I used in that example to understand each step. So I'm also entering the same source vector, so I'm getting some answers. So let's start from the beginning. First, my code is finding the augmented matrix by just augmenting the original A with B, like here. Then my next step should be finding the S. So S will be my code will find the S in the loop. The S1 is 4.21, then 10.2, and then 1.09, same like these. And then in the loop I will divide each entry of the column below the pivot entry and the pivot entry with the corresponding S, and it should be stored in D. So my D has like 0.5 0.5012, then 0.393, and then the 1. So the largest entry is 1 in this case, and based on this there will be row exchange, row interchange process, and you can see the first and third rows are interchanged like we interchanged here. So the code is interchanging it now, and after this my new S are coming, and the new S are here 10.2 and 4.21. Just focus on S2 and S3 because we are going to utilize these S2 and S3 only, and S2 and S3 is 10.2 and 4.21. And then in the next step, after identifying the S, now I am applying the multiplier thing or Gauss elimination method. So I am making each entry 0 below pivot entry, so you can see here. And after this my new D will come, and I will decide which row should be interchanged based on these D's, and after swapping the rows I'm getting answers. And you can also match your final matrix and then final answers with the answers in that document, and you can see from here this is my final matrix, which is the same as the matrix in the code, and these are my final answers, which are the answers obtained in the code. But the good thing about this code is that this code is general, so we can solve any n cross n system from it. For instance, if I take a random matrix of integers whose integers are starting from 1 to 10 and the dimensions of matrix is 8. So I am storing a 8 cross 8 system in A matrix, and then 8 cross 1 source vector. So you can see my code is still working, the code of scaled partial pivoting, and it is giving me the answers. So that's all about making the MATLAB code of Gauss elimination with scaled partial pivoting. See you people in next video.